Hi, everybody. It's Professor Mitchell, continuing with Chapter 8. Today, we're looking at Section 8.7 on numerical integration. So numerical integration is used to approximate an integral when you can't find its exact value. And there are two situations where that could happen. Of course, normally the way we try to evaluate an integral is to use the fundamental theorem of calculus, where you find an antiderivative for the given function f of x, and then plug in b, plug in a, and subtract, right? So the first situation is where the function f of x has no elementary antiderivative. There are lots and lots of functions that have no elementary antiderivative. Literally impossible to find an antiderivative for that function. Some examples are the sine of x squared, 1 over natural log of x, and the square root of 1 plus x to the fourth. The other situation where you can't find an exact value for the integral is when the function comes from experimental data and doesn't have a nice formula like f of x equals x cubed plus sine x. For example, if you wanted to estimate the area of this lake, I don't know how to find a function whose graph matches. First of all, this would have to be at least two separate functions, right? Because it fails the vertical line test. So even if I split this into, say, a top half and a bottom half, I don't know off the top of my head a function that exactly fits this curve. So we can use numerical integration to get a really good approximation for the area of that lake. All right, so we're going to be looking at two different kinds of approximations in this section. The first kind is called trapezoidal approximations, or the trapezoidal rule. So the idea behind this rule is that you take your function and take the interval that you're integrating that function over, you chop it into little subintervals, and then you fill in the space under the curve with trapezoids, like you see here. And I'll spare you the details, but it's not too difficult to show if you know the area formula for a trapezoid, that the area of, for example, this trapezoid right here, the second one, is 1/2 times y1 plus y2 times delta x, where delta x is the width of one of these little subintervals. All right, so that leads to this formula for the trapezoidal rule, the trapezoidal approximation. To approximate the integral from a to b of f of x dx, use t, which is equal to delta x divided by 2 times the sum y0 plus 2y1 plus 2y2 plus yada, 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 plus 2 times y sub n minus 1 plus y sub n. All right. So these y's stand for the value of the function at the endpoints of those subintervals. And of course, we're going to do examples, so you'll see exactly how this works. This might be a little bit difficult right here to digest. So we have these partition points, x0, x1, x2, all the way up to x sub n. And again, delta x is the width of one of these subintervals, all right? So I think the best way to help you understand this formula and all this notation is just to look at an example. But first, I want to show you that if you have a graphing calculator, which is recommended, that makes it very easy to get the values of these y's that you need for the formula. And so I'm going to use this in each example that I do. I'll just talk you through the steps right now. So the first thing you do is hit second table, which brings you into table settings. And then it's going to ask you for a value of table start and a value of delta table. So set table start equal to A, which is the lower limit of integration, and then set delta table equal to delta x, which again is b minus a over n. Then go into the y equals screen and put in your integrand, whatever function it is you're trying to integrate, and then press table. And the first n plus 1 values under the y1 column will be the values y0, y1, up to y sub n that you need to put into the formula. All right, so here's the example. We're going to estimate the integral using the trapezoidal rule with n equal to 4. And we're estimating the integral from 2 to 4 of 1 over s minus 1 squared ds. Okay, so let's talk about our notation a little bit, and then I'm going to go over to the graphing calculator to get the table. So in this problem, a is equal to 2, and of course b is equal to 4. And they told me n was equal to 4. So that means delta x is b minus a over n, which is 4 minus 2 divided by 4, which is 2/4, which is 0.5. You're going to see I'm very big on decimals in this section. I just realized I forgot to share my tablet. Okay, I thought about doing that part of the video over, but I haven't really gotten too far into the problem yet. Okay, so once again, a is equal to 2, b is equal to 4, and n is equal to 4. So that means that delta x is b minus a over n, which is 4 minus 2 divided by 4, which is 2/4 or 0.5. So the idea behind that, the notation in this section is a little intimidating. It means that we're taking the interval from 2 to 4 and we're chopping it into 4 pieces. So that means that the partition points x0, x1, x2, x3, x4 are going to be 2. So the number a is also known as x0. And then x1 would be 2.5. x2 would be 3. x3 would be 3.5. And then x sub n would be 4. And x sub n is also known as the number b. All right. So now let's go over to the graphing calculator. Let me just tell you before I get there that I am going to set table start equal to 2, and then I'm going to set delta table equal to 0.5. Okay, so let's go over to the graphing calculator. Okay, here we are. So the first thing I'm going to do is hit second table. That brings me into table settings. And remember, I said I was going to set table start equal to 2 and set delta table equal to 0.5. So now what I want to do is go into the y equals screen. And I'm going to set y1 equal to 1 over, I can't use s on here, so it's okay to use x minus 1 squared. All right, and now I'm going to hit table. All right, so the first 5 values corresponding to the values of x from 2 to 4 are the values of the y's that I'm going to put into my formula. So y0 is 1, y1 is 0.444, y2 is 0.25, y3 is 0.16, and y4 will be 0.111. All right, so let's go back to the tablet. Okay, so here is the trapezoidal rule formula. delta x is 0.5. So we're going to say 0.5 over 2 times, and now I'm reading the y values off my calculator. Y0 is 1. Y1 is 0.444. Now your online homework will specify how many decimal places they want, probably. So what I would recommend, let's say that it asks for, you know what, let's say it asks for 4 decimal places. Then a good rule of thumb is to use at least 5 in your calculation. So I'm going to call this 0.44444. Y2 is exactly 0.25. Y3 is exactly 0.16. And Y4 is approximately 0.11111. All right. So now I'll crunch those numbers. All right, so to 4 decimal places, what I get for that is approximately 0.7050. All right. A little bit later, we're going to compare this value to the exact value of the integral. This integral happens to be one that we know how to evaluate exactly. All right, so we'll get to see how good an approximation this is. All right, so the other way that we're going to approximate integrals is using Simpson's rule. The difference between Simpson's rule and the trapezoidal rule is that instead of fitting up the curve with line segments and forming trapezoids, we fit up the curve with short stretches of parabolas, like you see in this picture. And in my experience, Simpson's rule tends to give a better approximation. And here's the formula for Simpson's rule. So one kind of interesting thing about Simpson's rule is that the value of n has to be even, all right, in order for this formula to work. So to approximate the integral from a to b of f of x dx, use s, which is delta x over 3 times y0 plus 4y1 plus 2y2 plus 4y3. So those interior terms from y1 through y sub n minus 1, the coefficients go 4, 2, 4, 2, 4, 2, da 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 da, and will always end on a 4 as long as n is even. And just like with the trapezoidal rule, y sub 0 and y sub n do not get a coefficient. The coefficient is 1. X0 through xn are defined just like before. Delta x is defined just like before. All right, so for this example, we'll estimate the integral using Simpson's rule with n equals 4. The integral from 0 to 3 of 1 over the square root of x plus 1 dx. All right, so going over to the tablet. All right, in this problem, a is 0, b is 3, and they told us to use n equals 4. So that means delta x, which is always b sub a, b minus a over n, will be 3 minus 0 over 4, which is 3/4, aka 0.75. All right, so now I'm getting ready to go over to the calculator. I'm going to set table start equal to 0, and delta table is going to be 0.75. All right, here we are. So first I'm going to hit second table. And I'm going to set table start equal to 0. I'm going to set delta table equal to 0.75. Now I have to put the correct function in the y equals screen. So that's going to be 1 over the square root of x plus 1. All right, so now I'll hit table. And the first 5 values that you see there, 1.75593, I'm going to call that 0.63246, 0.55470, and 0.5. Those are the values of y0 through y4. All right, and here is our Simpson's rule formula. So we're going to go 0.75 over 3. And then reading the y values from my table, it's going to go 1 plus 4 times 0.75593 plus 2 times 0.63246 plus 4 times 0.55470 plus y4, which is 0.5. All right, and after crunching those numbers, what I get to 4 decimal places is 2.0019. All right, so that brings us to error analysis. And the idea here is that a method for estimating something isn't really too valuable unless you can get an idea of how good the estimate is. So this theorem addresses that for both the trapezoidal rule and Simpson's rule. All right, so the first part talks about error estimates for the trapezoidal rule. If f double prime, the second derivative of f, is continuous, and m is any upper bound for the values of the absolute value of f double prime on the interval from a to b, then the error e sub t in the trapezoidal approximation of the integral of f from a to b with n subintervals satisfies the following inequality. And by the way, don't ask me to derive this, because this is not a let me spare you the boring details situation. This is more of a I don't remember how to do it situation. All right. I think I may have done this. I can't remember. The absolute value of e sub t is less than or equal to m times b minus a cubed over 12n squared. All right, so that's kind of an interesting formula, not one that I would recommend memorizing. Okay, for Simpson's rule, it's kind of similar, except it goes by the fourth derivative. When have you ever used the fourth derivative for anything? If the fourth derivative of f is continuous, and m is any upper bound for the values of the absolute value of the fourth derivative on the interval from a to b, then the error e sub s in Simpson's rule approximation satisfies the inequality absolute value of e sub s is less than or equal to m times b minus a to the fifth over 180 n to the fourth. So I kind of wish that I could see the derivation of especially this inequality. I'm kind of curious where that 180 comes from. But the short answer is I don't know. Right? Okay, so here's the example I have for you. We're going to go back to example 1 and find an upper bound for the absolute value of e sub t. And then we're going to evaluate the integral directly so that we can find the exact value of E sub t. Then we're going to do the same thing with example 2 and Simpson's rule, error estimate. All right, and then this is what I really like to use this formula for. Estimate the minimum. Okay, so the idea here is, let's say that you know ahead of time that your estimate has to be good to 4 decimal places. All right, so this method will allow you to do that. Estimate the minimum number of subintervals needed to approximate the integral with an error of magnitude less than 10 to the negative 4, first by the trapezoidal rule and then by Simpson's rule. So the integral is from -1 to 1 of cosine of x plus pi dx. And I'm going to switch over to the tablet where I've got this all set up. All right, so the integral in example 1 was the integral from 2 to 4 of 1 over s minus 1 squared ds. And we want to find an upper bound for the error in the trapezoidal rule. Okay. All right, so remember in that example, well, A is 2, B is 4, and we used n equals 4. Okay, so the main thing that we need to figure out right now is m. So let's take our function, which is f of s equals s minus 1 to the negative 2. And I'm writing it like that because I'm about to differentiate it. The first derivative of f is negative 2 times s minus 1 to the negative 3 times the derivative of s minus 1, which is 1. So then the second derivative of f is 6 times s minus 1 to the negative 4, also known as, oops, 6 over s minus 1 to the 4th. So what we need to do to find m is look for an upper bound on the magnitude of that expression on the interval from 2 to 4. Okay. So I'm going to say something right now, and I want you to think about it. The question is, where in the interval from 2 to 4 is this expression largest? And the answer is at s equals 2, right? A fraction is largest where its denominator is smallest. And the smallest you can make this denominator in the interval from 2 to 4 is at 2, right? So m is going to be the absolute value of f double prime at 2. Now I'm throwing the absolute value in there because I don't want you to forget that you need it in general. This expression happens to never be negative, so I don't have to worry about it here. 6 over 2 minus 1 to the 4th is 6. So I'm going to use that as the value of m. So now we're ready to find our upper bound on our error. And I did not leave a blank page after this one, so I'm going to have to steal some of this space. I think we can finish this up over here. All right, so the absolute value of E sub t is going to be less than or equal to m, which is 6, times b minus a to the 3rd over 12n squared. All right, so let's see, what does that come out to? We have 6 times 2 to the third over 12 times 4 to the second. And I think rather than reach for my calculator, I can just whittle this down. So this is an 8 and this is a 16. So let's cross those out and leave it 2. 6 into 12 goes 2. So it looks like the upper bound on our error is 1/4. All right, so this estimate, or the trapezoidal rule estimate, is guaranteed to be within 1/4 of the actual value of the integral. Okay, so the second part of the question was sort of to test that. So now we're going to find the exact value of this integral, and then we can calculate the actual error. Okay. Now, the point of the trapezoidal rule, or part of the point of the trapezoidal rule and Simpson's rule, is to be able to use it on integrals that you can't evaluate exactly. All right, we're doing this just for practice. Okay, so once again, I'm going to write 1 over s minus 1 squared as s minus 1 to the negative 2. And then by the backwards power rule, that comes out to s minus 1 to the negative 1 over negative 1. All right, so of course, s minus 1 to the negative 1 is 1 over s minus 1. So when I plug in 4, I'm going to get negative 1/3. When I plug in 2, I'm going to get negative 1. The exact value of this integral is 2/3. Now remember from example 1 that t was the trapezoidal rule estimate was about 0.7050. So that means that the actual error is 0.7050 minus 2/3. I'm not going to try to do that math in my head. That comes out to about 0.0383. Which is less than 1/4, actually a lot less than 1/4. But remember, the upper bound is exactly that. It's an upper bound. It's guaranteeing that the error is no more than 1/4. All right, and often it's a lot less. Okay, so that upper bound is just sort of a worst case scenario. All right, that takes care of the first part of that example.